Hello everyone, this is Sahith Reddy Mudiganti. I'm a master's student in civil and construction engineering at Western Michigan University. I'm going to present a new method of quantity takeoff by using pseudocode for BIM-based wall components, which was done as part of my advanced design project under Dr. Jeon Sung Zhang's supervision. Students pursuing the design option for the graduate degree in civil engineering will enroll in this course when conducting the design project. Students basically enrolled in this course will work under the direction of their graduate program advisor, and my advisor was Dr. Jeon Sung Sang. Also, I would like to take this as an opportunity to thank my advisor, Dr. Zhang, for helping me out in doing this advanced design project and bringing out the best in me. I've explored my knowledge in the IFC data, and Professor also gave me a chance to explore softwares like BIM 360 Glue and Solibri Model View. Basic idea for my design project was to develop a pseudocode for a wall component by traversing the IFC data for that component to get quantities like length, height and thickness, from which area and volume are computed, which helps in estimation. As we already know, quantification is the first step in cost estimating, which also takes most of the time in creating a cost estimate depending on the type of project. So by automating this tedious task of quantifying allows the estimators to use their time instead to focus on other high value project specific factors such as identifying construction assemblies, factoring risks, etc., which are essential for the high quality estimates and gives an accurate output. So to discuss about all the things that I have done during the course of my advanced design project, firstly I've explored two software platforms which were BIM 360 Glue and Solibri Model Viewer. And after that, I've done manual quantity takeoff for an office building using BIM 360 Glue software. This was basically done in Excel. So let's go ahead and look how it looks like. So over here, as you can see, manually the quantities like length and area for different components like walls, doors and windows have been taken out, which further can be used for estimation. So similarly, quantity takeoff was done using the Solibri Model Viewer, basically to compare the efficiency between these two platforms. So this is the quantity takeoff using Solibri Model Viewer. As you can see, I have grouped the doors with similar areas under one column. So you have two doors of 15.02 square foot and three doors of 13.35 square foot. This is a quantifying of doors, and similarly for railing, stair and suspended ceiling, walls, windows. This would help an estimator in estimation. So this helped me in having an understanding of the quantity takeoff process, which helped in automating the quantity takeoff later during my project. So to start off with, I've started using a wall that has been created in Revit and has been converted into an IFC file, and I started analyzing the IFC data for this wall component. So this is the wall that have been created in Revit, and I've started to analyze the IFC data for this particular wall. So to give a small introduction about the IFC data, the industry foundation classes has been developed for exchanging and sharing the data among all the IFC compliant software applications in the AEC industry. It was first developed in 1994 by the Industry Alliance for Interoperability, which was a consortium formed by Autodesk. Later in the year 1997, in order to continuously develop the IFC data standards, this consortium became the International Alliance for Interoperability, which now is a non-profit organization called as Building Smart. So after picking a wall and creating that in Revit and analyzing the data, I've started analyzing the Cartesian points of the wall IFC data to obtain the quantities like length, height and width, but no significant output was obtained except for height because of the structure of the IFC data. So these are the Cartesian points of that IFC wall. As you can see, you can only get the height from this data. These Cartesian points were plotted in a 3D space to analyze the structure. So as you can see, you can get the height from this, but you can't get any other dimensions through these Cartesian points. And later I started to study the structure of the IFC file to understand how to get the quantities from that. So after that, I've started to study the structure of the IFC file and try to understand the structure. This is a sample file while I was trying to understand each entity of my IFC data. Then I came out with the structure in order to do the quantity takeoff. So let's see the IFC data structure for the experiment wall. So the first entity we'll be looking at is IFC wall standard case, which has all these subtypes. I'll be showing the entities which are required to obtain height, length and thickness of the wall. The first one would be IFC extruded area solid, which is number 176. And through this we can obtain the height of the wall by observing the fourth subtype of this one. And this has a subtype IFC rectangle profile depth, from which we can obtain the length, which would be 10.14583 for this particular wall, and width would be 0.40625. Through this, area and volume can be computed. And now, since I had an understanding about the structure of the wall component, I've developed a pseudocode based on the structure. So let's go ahead and look at this pseudocode. So to explain this in an easiest way, first you are trying to import the wall file, and then you are searching for IFC wall standard case entity. After that, you are trying to look for IFC extruded area solid entity, and through this you can read the height and then print the height of the wall, and read length and width from IFC rectangle profile depth entity, which would be the subtype of IFC extruded area solid. And through this entity you can get the length and width, and then later you can compute the area and print the area of the wall, and compute and print the volume of the wall. So once the pseudocode has been developed, this has been tested on other walls. So the pseudocode output for the test model is this. You can see the height was 14 feet, length was 60 feet and thickness was 0.406 feet, and the area and volume are 840 and 341.04. When this wall was viewed in Solibri model viewer, the quantities obtained were: area was 840.00 square feet, which was same as the output that we got from the pseudocode. So through the results obtained through testing of pseudocode, it can be said that the results were consistent. So in summary, I'm going to discuss about the methodology of the research. So to automate the quantity takeoff process using this particular method, you have to first determine the object for the quantity takeoff, and then study the structure of the wall in IFC, and develop the quantity takeoff pseudocode, and test the pseudocode on other objects and verify the accuracy. This method has proven effective for wall components. This research work can be extended by analyzing how different software platforms analyze the IFC data of this wall, and the pseudocode can be updated based on that.